Hi, welcome back. Now I want to introduce to you Alberto Zuin. He is talking about geo-distributed data centers the DNS way. So have fun.
Okay, thank you. Hello to everyone, and many thanks to the people of OpenNebula team. So, let me introduce myself. I'm Alberto Zuin, and I am the CEO and CTO of a UK company, Maui.co. And is a company founded last year, so I really new. At Moi.co, we are specialized in creating multi-data center infrastructure for web and mobile application, and are also we have also some developers to help in creating application that can really on a multi-data center infrastructure. Now I want to speak you how to distribute service across multiple data center, and to do that I want to illustrate the three experience that we made in the last years. At the beginning, I will illustrate how we manage the OpenNebula installation here at Mod.co. And I think it's an interesting case study because we have multiple data centers distributed worldwide instead of big one, but very, very small. In the last part of the presentation, I will talk you about 3 other case studies of application distributed in multiple data centers. Therefore, I can give you an idea how you can develop an application homed in multiple data center with OpenNebula, and how to use, of course, Moi.co DNS to be online in case of a data center failure. So let's talk about my experience with OpenNebula in the past. Just a little history of my life. I worked for many years as a consultant for cloud providers, and sometime from the beginning when I had to develop a new cloud infrastructure, I always choose OpenNebula. Why? Because at the beginning of my life, there was eucalyptus, but I found it very limited. And at the beginning, there was OpenStack, but was too young. Now, the same, eucalyptus was disappeared, and OpenStack is too big, complex for my customers. At that point of my life, when I was only a consultant, my experience with OpenNebula is the same of everyone in this room, I think. So installation with large infrastructures, with a SAN or a shared storage, a cluster storage, usually 1 or 2 racks of big servers. But about 3 years ago, we had a little problem. All was great and all was working well, but we experienced some fault at the network level of our primary data center. So we went offline, but even our infrastructure was up and running. So this is the moment. This was the moment when we start thinking about creating a multi-data center architecture, and how to orchestrate the traffic between our POPs. At Mod.co, we realized we have created an advanced DNS server similar to Amazon Route 53, which is released on premises. Now we are working in creating a cloud edition for reseller, and we use actually OpenNebula to manage this infrastructure. Currently, we have our server in 4 data centers around the world. There are 3 European data centers because our immediate target clients are in Europe. One is our historic Italian data center in Padua. This is a city not far from Milan. We have a direct link in fiber optic to Mix, which is the Milan Internet Exchange. And one is in Rome, directly connected to NAMED, which is the other one, Internet Exchange in Italy. We have other two data centers. We have a presence in France, for Europe, and one in Kansas City for USA. And next year we will expand I think in Singapore for the next Far East. So in every data center we have placed, a minimum of 2 servers. Every server has a local storage with SSD disk. So we don't have to share this component, the storage component in any way. So no SAN, no replica via DRDB, etc. We have only 4 SSD disk in every server, configured in RAID 10. Very simple. So in every data center we have a physical server with a VM with a MongoDB. Another VM is configured with Quagga. It's our routing packages, which handle BGP and OSPF routing. So we have another VM with the API server, and at minimum of 2 VM with the DNS server. The second server and the next are the physical server are only for DNS. Virtual machine, and we are evaluating to configure it in auto-scaling with one flow and one gate to handle peaks. So don't want to bother anymore with the details of our infrastructure, but I think it's important to understand why we don't have a shared disk in every data center. This is because the entire infrastructure is resilient to the fault of an entire data center or more. Okay. Coming to OpenNebula. So we have a total of 4 data centers in the world. So this is the typical use case of a federation setup. With this kind of setup, every data center, and so in our setup is every server in every data center remains independent, but each one talks to the masters via RPC. So whatever can be used to control the others via Samstone or command line. So it's easy for us to manage the infrastructure because we have only one entry point where we can control the entire infrastructure. So we don't have many tabs on our browsers or many SSH sessions. Also, this is important for us because it helps us in the updating. We will see that in some minutes. So the installation and configuration of OpenNebula Federation Mode is simple. It's well documented on the OpenNebula website. Just to talk a little about that. At the base of every server there is a KVM for virtualization and a MySQL database. And in every server, in every physical server, there is a complete OpenNebula installation. So after the installation, we have all packages installed in every physical server, but we have to choose to promote one of the server as a master. Okay, we choose the installation in Padova data center is then our master. So we configure the MySQL server as a master and the other MySQL server as a slave that server. Not all tables are replicated across this configuration of MySQL server, but only the ones that is important for OpenNebula. So the users, the group, the zone, and the DB versioning, and the ACL. So it's very limited, the replication of MySQL. To do that, we have to declare this table inside the MySQL configuration file, my.cnf. The other things we had to do is to configure correctly the OpenNebula daemon. So we have to do that in the 1d.conf file, and we have to declare if a physical server is a master or a slave, and in case of slave, if what is its ID, and the RPC URL of the master server. This is because the user part, the group part, the authorization part of OpenNebula went only on the master server. So if, for example, we had a user on a slave server, this call was intercepted by OpenNebula before doing on the local database, and is sent to the remote server via an RPC call. And after that is replicated via standard MySQL replication server. About the federation, the last things I want to say you is at the August of this year was there is the new 4.8 version, and in September we updated the whole infrastructure from the old 4.6 to the new one. At the moment, we haven't switched to 4.10, but we plan to do that in the beginning of next year. And the update process was like a charm, because we have no downtime at all. And all the two versions coexist during the upgrade without any problem. So, in the fact that the 5 replicated tables are retrocompatible, so we started the upgrade process on our master server, and after that we updated all the other one. In version 4.8, there is a small interesting feature about federation, and now all the log produced by the OpenNebula daemon include the zone ID. So we start to send all the logs generated by OpenNebula to a local syslog server instead of the classic files, log files. So we have created a virtual machine in every data center with syslog ng daemon. This machine catches all the logs by OpenNebula and stores in a MongoDB database. We choose to have a syslog server, syslog machine in every data center because syslog works in UDP, and so the packets are very, very, very delicate. So a little plan for the future, one flow and one gate. As we said, we are going to evaluate this system to autoscale our core DNS system, virtual machine. So to be precise, do you know what is Anycast? Yeah. For not many people. So Anycast is it's a routing protocol where the same IP address is configured in more than one place. Okay, we use Anycast in two ways: from the external with the BGP, and from internal with the OSPF, which are routing protocol. From external point of view, we announce two distinct public classes, public IP address classes via BGP, and to our upstream of every data center. So, for example, people who query our DNS from USA comes to server in USA. People that query our DNS from Europe go to the server in Europe. And it's to have the smallest possible latency time. Also, if a data center goes down, all the query go to another data center because the announce goes down and the data center is isolated from the rest of the world. On the other side, from inside our infrastructure, so the query arrives to our Quagga routers thanks to BGP. Now there is a simple net rules that forward all traffic, all DNS traffic, to a single internal IP address. Okay. This is the key of OSPF. So every DNS virtual machine instance has its private IP address, and this address is configured by OpenNebula contextualization system, and also has a secondary IP address. It's a /32 address configured on the low interface, the local interface. In all the server, all the DNS server has also a Quagga router inside, which only announce this IP address to the core Quagga router inside the data center. So the core router has many ways to reach the static IP address /32, one routes for every DNS server, DNS virtual machine. This is the key, because if you want to plan to go to an auto-scaling system with one flow and one gate, it's simple. Start a new virtual machine. This machine announce itself by OSPF with this static IP address, and is automatically added to the pool of local server. Okay. The last things we want to talk about is our future plan with the OpenNebula system. So at the moment, sorry for that, we integrated our Moi.co DNS system with the OpenStack authentication, because our first customers are on OpenStack. But also we have integrated it just a little with OpenNebula using the LDAP daemon. Okay, because we have a customer near Rome, which is ongrid. It's a virtual machine provider, not really a cloud provider. It's like Linode or DigitalOcean, just to understand. And he already has an infrastructure with an LDAP database for WHMCS is a tool to for an internet service provider to sell services, standard service like websites hosting and so on. So we use this database, the LDAP database, to really also the DNS system. In next year, we plan to integrate a little better with OpenNebula using the MySQL directly, the MySQL database of OpenNebula. And also, our idea is to create a community edition. This community edition will be free and totally open source, but with not all the capabilities of our standard product. The idea is to create a system similar to one flow, one gate, just to understand. So ready to use a virtual machine which takes from the OpenNebula contextualization system all the information and automatically create the record on the DNS using the contextualization system. So, coming to some use cases. The first use cases of a federation system with OpenNebula and our DNS system is Abruzzo Web. Abruzzo Web is a news portal, an Italian news portal, which is made in PHP and at the beginning stay on a cheap, very cheap server, monolithic LAMP server in Italy. So when I started to work with these guys, we started to scale a little this system, and we add another server inside this data center, and we helped the guys to rewrite a little its application to stay on two servers. Okay. All works well, but at some point the cheap collocation provider starts to have some problems. First was a fire in the UPS room, and this caused a blackout of the entire data center. And after this problem, there was some problem on network switch. So he asked me an opinion because he wanted to go away. But there are three problems because it's a server are rented, so it's impossible to simply go in the data center, shut them down, put in the car, and go into another one. All collocation that I can recommend are too expensive for this customer, and this guy is very impulsive. So there is the risk if for me in case of a failure of the new data center. And I didn't want any problem in my life. So I recommend him to not change the actual supplier, but rent another server in another collocation provider and in another country, and distributes the web news portal on 3 physical servers. Okay, not only 2. Is very happy and is still a customer of mine. The second case studies I want to talk you about is Zotzel. Zotzel is an application which helps salesmen all over the world, and it uses primary emails to communicate with customers. So they have the necessity for a very reliable SMTP services. also, they have an internal server, a small internal infrastructure inside the company. With the RT is request tracker, is a software for some ticket support request, and this software is integrated via email. So they have two problems. The first is to have a distributed infrastructure of MX server around the world, because there are some little problem, for example, with South America for about routing. So having a server in different country is better. And also, this is interesting, because they simply create a record on the DNS server is called a latency or a GeoDNS. When, for example, when a mail server in the USA has to contact zotsel.com domain, the DNS return a pool of MX server, where the one with the most higher priority is the one in USA. And obviously, when a mail server in Europe has to talk with zotsel.com, return another pool of MX server with the one with the bigger priority is the one in Europe, and so on. The second problem is all the MX server has to talk with the server inside the company. The company, the internet connection of the company is an internet connection with a static IP address, but is not it's a standard internet connection. So they wanted to stay up also in case of fault of this kind of this internet connection. So they have another connection, a backup internet connection, but with a different IP address. So what they have is another record, another DNS record, configured in high availability routing policies. So when the primary line goes down, all the traffic is switched to the backup line, simply. Third case study is about log retention. It's only an Italian problem, I know. Because in Italy there is a very severe privacy legislation. So an ISP needs to store only some data of the log, for example, the radio session and the SMTP session, but can't, for example, can't store data about the navigation. He can store this data for a maximum of 12 months, encrypted with strong authentication and with an audit log to know what operation was made on log, because the legislature wanted to be sure if a sysadmin goes mad and deletes all data, the ESP can don't lose anything. Okay. The solution was a local syslog server for every ISP that takes all the data, periodically encrypt with the PGP, which is a strong authentication system, apply a timestamp, and send it to different storage facilities. So we have two different storage facilities in two different data centers in a shared nothing architecture. When I say shared nothing, is really shared nothing because there are two different sysadmin for every data center. So the sysadmin A don't have any access on data center B, and vice versa. So if I go mad or make a mistake, there is another point of return on the other data center. Okay, every data center has a virtual infrastructure we made with OpenNebula, with a couple of servers for the storage in MongoDB, and an API server that receives files from the remote customer from the syslog servers. And if an ISP needs to get a file, it has to log in to a web interface where he can search the file using some criteria and download it. But we have two infrastructure where he can access on data center A or data center B. It's not a problem because the two data centers are independent. They share only a distributed Redis database with the session and of authenticated user. And at the top of that, there is our DNS that balances the traffic between the two data centers and exclude the one in case of a fault. So, at the end, for you, if you want to create a distributed application, what do you need? The theory is to think as a stateless system, not stateful, because DNS is a stateless protocol. The first rule is easy. Think to distribute everything. You don't have a single data store for all the infrastructure. Every system must have all the needed data in local. So, for example, for OpenNebula, the OpenNebula team choose to have a MySQL database configured in master-slave asynchronous replication for a federated data center. No? And this is the correct way to do that because every data center know all the information, and the asynchronous replication can stay on multiple data center. Another solution like a MySQL cluster is not correct for this kind of operation because it's synchronous. If you think synchronous, all your application can stop in case of a fault. Okay, so this is the second lesson. Think only in asynchronous. The third rule is share the session, because DNS is stateless. When you create a web application, normally if you want to authenticate a user, there is a session stored locally in your web server in some way. For example, the easy, it's a file inside a temporary directory. Don't do that because it's impossible to relay an application using this kind of session in a multi-data center infrastructure. You have two options. The first is share the session between application server using a common database. In our experience, Redis it's a good choice because it's very, very powerful for speed. The second option is to use a single senior system like OAuth 2 to authenticate the user. Okay, this indication remain valid if you decide to stay only in one data center with multiple servers. And is not a problem. If you project your infrastructure in this way, works also only in one data center. Okay, if you have any question, I'm here.
One moment.
Hi. Does your DNS service are they reachable over IPv6 as well as over IPv4?
Okay. he asked me, correct me if I don't understood well, if this kind of configuration works on also for office purposes. No, no. IPv6. Ah, okay. I don't hear well. About IPv6, okay, it's not a problem for us, IPv6, because for us it's only a record. Okay, it's a different record than the classic A record for IPv4. So the IPv6 protocol is implemented from the beginning, from the first release of our DNS system. So it's not a problem at all. We have other limitation. At the moment, we are working hard to support DNSSEC, but IPv6 is not a problem.
Okay. Any questions?
Yeah, at the beginning of our adventure, we try some other open source option. In fact, we tried two options, bind and the power DNS. Bind is not useful for us because we need dynamic DNS, and bind handle it in a very strange way because it has an application that's to change the IP address of the record. If we want to update a record inside bind, we have to restart the services to reload old zone, or just to be very simple. Power DNS was our first option before going to create our DNS system with the Scala. We start with the Power DNS using there is some backend with Power DNS you can use. We use the pipe backend. I remember correctly. Power DNS takes all the traffic, all the DNS traffic, do the minimum of a require, and send all the traffic to another daemon. In our case, was a C++ application to interact with our MongoDB storage. But at the end, we choose to create a new DNS server because we have some limits with the Power DNS. The first limit we found in Power DNS, it's a strange thing because we had an attack, a denial of service attack, which multiply its power because was made on UDP packages. So we choose to close the packet size of UDP packets and send all the query on a TCP, just to avoid any problem with denial of service attack. And this kind of configuration can't be made with Power DNS, with bind on other systems. So we choose, this is the first reason because we choose to create our DNS system.
Okay, thank you. We are delayed. So we have a 5-minute break now. And thank you very much.
Okay, thank you.